So this is part of our Cfe Higher Physics particles and waves. So really, it's Cfe Higher Physics particles and waves, and we're just quickly looking at some extra bits relating to diffraction gratings. And the main reason for this is I felt that in the other section it had gone on too long, and there are a few more points that we really did need to discuss. First of all, you can get questions like this, where you're asked about the spacing of the dots on the screen, and the question says the diffraction grating has 100 lines per millimetre. The diffraction grating of 100 lines per millimetre is replaced by one with 400 lines per millimetre. How does this change the pattern on the screen? Now, you've actually done this, and I came around to make sure that you could actually see this and observe it with your own eyes, but I think it's important that when you're under pressure, you don't rely on your memory. So an alternative question would have been, how does this change the angle theta in the sort of n lambda d sine theta, or the position of the first maximum, or something like that? So there's quite a few different options, but we're all relating to making a change and asking for a change in the sort of trend of what's going on. Okay, so let's start off with the equation. That's at the heart of the whole business. If you can remember, this is our diffraction grating equation, you can then use it to solve all these issues. Okay. Now remember, if you don't change the source of light, then the n lambda part is going to be constant. So whatever's on this side is going to have to equal this value. And so if you're looking at the same line as in the first maximum, or you're still looking at, say, the second maximum. So if you don't change the n and you don't change the wavelength, it's the same light source, the same laser, then, so you're not going to change the laser and you're not going to change the spot. Then this is really quite simple, in that if the value of d is going to increase, then the value of sine theta will have to decrease, because this side of the equation is going to have to remain equal to this, and this is constant. So if you change the d, if the d gets up, the sine theta is going to go down. And there's only one way for sine theta to go down, and that is theta goes down. So, have we gone off the... Right, okay. Now, what does increasing d mean? So increasing d means, remember, d is the slit separation. So you've got millions of slits, and perhaps millions is an exaggeration. You've got hundreds of slits. And the separation between two consecutive slits here, that is our d, the separation between two consecutive. So when you're looking at the slits on the thing, you're saying, okay, here's the distance between two slits. That's d. Now, if d gets bigger, you have less lines per millimetre. If you space these out part apart, then in any given length you'll have less. This is an important point, is the kind of reverse or inverse relationship between d and the number of lines per millimetre. So if your d goes up, you've got less lines per millimetre, and the angle will go down. Now, how you saw this would have been, I gave you a fairly probably cheaper diffraction grating at 100 lines per millimetre, and it doesn't separate the dots out much, because they say the d is actually relatively big, so the sine theta is small, the angles are small, so the laser's only gone through a small angle to get to, say, the first maximum. Now if I say, okay, let's use a better one, I've got 400 lines per millimetre, and what's happened here is, look, the central maximum is in the same place, but the first maximum is now miles over here, because d has now, by having 400 lines per millimetre, the space between each line has gone down a lot. So now d has actually gone down, and so the sine theta goes up, and the angle theta increases. Okay, so the rule there is more lines per millimetre gives you a more spaced out pattern. Okay, and for more lines in a millimetre, your d needs to get smaller. Okay, what's the next bit? Now, so more lines per millimetre gets to a more spaced out pattern, i.e. theta increases. Okay, let's look at changing wavelength. Now, if you're going to change wavelength, that's kind of implying that n and d are going to remain constant. So if you're using the same, so if you're going to change from, say, a red laser to a green laser, Okay, how's that going to change the pattern? Okay, well, I've just started off by rearranging the equation here and saying, okay, let's bring the d over to this side. So d appears on the bottom there. And so I'm interested in what happens when I change wavelength. So now I'm going to say that the number of lines, sorry, the particular line on the screen that we're looking for, say the n equals 1 maximum. So the particular spot or line on the screen we're looking for will be constant. If the d is constant, i.e. I use the same diffraction grating. So how do I keep the d constant? That basically means I use the same grating. In fact, I probably shouldn't use grating. I probably should use diffraction grating every time so really I should have the word diffraction in there because I should use diffraction grating as the word. I shouldn't start splitting it up. Okay, so just think about this. Now here we've got that if these two remain constant, if lambda goes up, then sine theta has to go up. Okay, so these two aren't changing. If lambda increases, sine theta increases. Now how do we increase lambda? We increase lambda by going from a small wavelength, colour like blue, to green. Going blue to green is increasing the lambda, increasing that wavelength. And if I go from green to red, I'm increasing it again. So if I've got the same diffraction grating and I go from blue laser to green laser to red laser, at each step I'm going to notice an increase in sine theta, which basically means the pattern is going to spread out. So I've drawn a little example here, which is perhaps, it's designed to show it quite practically. So you can see here, as lambda increases, sine theta increases. And if you don't remember that I would get my theta, maybe, I'm hoping you can remember that we got theta by having our diffraction grating like this, the laser beam coming onto the diffraction grating, and then that spot appeared on the screen, and the theta's there. So that's the theta for our n equals 1 line. Sorry. Now, if you do it with a laser, you get spots. If you do it with another light source, like one of those gas discharge lamps we've got, and the beam from the lamp comes through a slit, you get lines. So I've been saying lines and dots interchangeably, perhaps confusing some of you, but it would be possible to have a screen on which, instead of seeing dots, you saw coloured lines. So you might see, say you were doing the sodium yellow spectrum, you might see a kind of messy line in the middle, and then you'd see a yellow line here and a yellow line here. And I know sodium yellow, so you'd have your, so it is possible if your light source is not a point source like a laser, it's actually an extended line source of light. You could have central maximum, your n equals 1 line and your n equals 2 line. And of course, if that was replaced with a laser, if I'm going to go to larger wavelength, so I'd probably have red spot, red spot, red spot, red spot, red spot. Okay, now, so that's a bit of an aside, but the key rule that I wanted to kind of get through was this idea that if the wavelength increases, sine theta increases, so theta increases. So this is your pattern. Okay? So the main thing to take away from today, or from this video, are the two diagrams, which is this one for 100 lines per millimeter, pattern close together, more lines per millimeter, pattern spread out, and longer wavelength, pattern spread out more. Okay. Okay, we're going to call that to an end there and continue with our course questions.